12.5 Dalton's Law of Partial Pressure. Dalton's Law of Partial Pressure. So Dalton's Law of Partial Pressure states that a mixture of non-reacting gases, the total pressure exerted is equal to the sum of all the partial pressures. So what does that mean in layman's terms? Well, think, for example, the atmosphere around us. And if we were to listen to a meteorologist state, okay, so today's temperature, the high was 23, and the barometric pressure for the atmosphere, let's just say, was 101.3 kilopascals. Now, if it was in fact this today, and we think about all the gases that make up the air around us in the atmosphere, understand that overall pressure is being exerted by all the various gases that are found in the atmosphere around us. So think of it, that the majority, right? So 78.1% of the atmosphere is made up of nitrogen gas. 20.9, again, depending on the resource, they can vary. But ballpark wise, these are the percentages that nitrogen and oxygen appear in nature. So now, if nitrogen makes up 78.1% of the atmosphere around us, it means that 78.1% of the daily pressure is actually, in fact, being exerted by nitrogen itself. Okay, so all the pressure that's exerted on us is directly related to the percentages in which these gases actually appear in nature. So one of the other things with regards to calculating pressure is understanding that including water vapor pressure in gas calculations. So one of the things is that you may collect many gases by allowing them to bubble through water into a container that is filled with water. Okay, unfortunately, when you're doing this, you are actually adding water vapor into that mixture. So when you're collecting some random gas, right? So you're collecting them, and one of the common ways to do this is to collect a gas in a beaker of water. When you are doing that, you are also collecting some water as a result of that. So you're collecting some water vapor as well. So to avoid error, the pressure that can be contributed by the water vapor must be subtracted when finding the pressure of a gas. Okay, so when you have that, we keep in mind Dalton's law of partial pressure, where the total gas pressure that's being exerted is based on the two gases in question. So let's say we're, in this example, we're collecting hydrogen gas. But when we collect hydrogen gas, we're collecting it in water. So as we're collecting in water, I don't know, do I have a picture here? I don't have a picture. I have it in my notes, I think. So when we're collecting the water when we're collecting hydrogen gas in water, what's happening is we're also creating water vapor at the same time. So when we're collecting the gas and we identify the pressure, understand that pressure, yes, we're collecting hydrogen gas. However, we are also collecting water vapor as well. So what we need to do is we need to subtract that water vapor from the hydrogen, from the overall pressure, to understand what the pressure is of whatever gas you're collecting. As in this example, we're collecting hydrogen. So what do we do? Well, there's a typical table that you would be using. Okay, so you would refer to this table, and whatever that gas happens to be, you would just subtract from this table. But I'll talk about that when we get to the sample problems in a moment. So let's look at some sample problems here. that I have at the end of this lesson. So there you go. That's how short this lesson really is. So here are the answers. Let's look at the steps to getting these answers. So we've got a container that holds 3 gases. We've got oxygen, carbon dioxide, and helium. The partial pressures of the 3 gases is 2 atmospheres, 3 atmospheres, and 4 atmospheres respectively. Okay, which means oxygen is 2, carbon dioxide is 3, helium is 4. That's what the respectively means for those who might not be so inclined to know that. Anyways, what is the total pressure inside that container when we mix all 3 of those gases at each one of their pressures? Well, all we do is to find the total pressure, we add up all the individual pressures of each one of those gases, and we get a total of 9 atmospheres when we add that all up. Nice and simple. Let's look at the next sample problem. Gas mixture contains 12% neon, 23% helium, 65% radon. If the total pressure is 116 kilopascals, what is the partial pressure of each individual gas? Well, turn each one of these percentages into a decimal, as we did here, and then multiply it by the overall pressure. And when we multiply them by the overall pressure, we will get each individual pressure. So here we have the pressure of neon, the pressure of helium, and the pressure of radon. And if you notice here, my final answer is based on the 3 significant digits that this answer should show. And if you add all these up again as a check, add all these up, and they should all add up to 116 kilopascals. Okay, last sample problem here, and this one really just kind of reiterates that table. So we've got 80 liters of oxygen is collected over water. So we're collecting oxygen gas, but when we're collecting oxygen gas, we have no choice but to also be collecting water vapor as well as we're doing the collection. So the atmospheric pressure in the room as we are collecting that gas is 96 kilopascals. So it's asking us what is the partial pressure of oxygen. But understand that that 96 kilopascals is part of the total pressure. And we want to find out what is the pressure of oxygen. But in order to do that, we need to now go back to this. Before we go, let's find out what that. So at 50 degrees Celsius, so we go back to that table at 50 degrees Celsius. Here it is. Okay, so at 50 degrees Celsius, the partial pressure of water is 12.3 kilopascals. So what we do in this sample problem, well, we've got our total pressure. We're trying to find oxygen, and we have the partial pressure that of water. So we isolate for the pressure of oxygen, take the total, subtract it by the pressure of oxygen to give us the overall pressure that is being exerted by oxygen alone. And because the calculation was subtraction, the least number of decimal places is what our answer needs to be. Understand that sometimes some of the numbers that you're going to see in a question, they don't really get utilized in your calculations. Okay, so please do be aware of these of this case. Okay, and in fact, actually, I made a mistake. This answer actually should have 2 decimal places. Sorry about that. I just noticed that now. 2 decimal places, and so I should include another 0 because, in fact, the only number I'm actually taking from the question is 96.00. I don't utilize that number, and I don't, in fact, use that number. This number was never part of our question. This number gets extracted as a constant, so we don't utilize constants when we are identifying least number of significant digits or even decimal places. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up,
Click on that subscribe to stay tuned to my new videos. Thanks for watching.